Welcome to MET 200 Manufacturing Processes and Material. In this lecture, which is lecture 7, we will be talking about polymers. This information can be found in chapter 8 of the book. We try to address all the topics here as much as possible. In this lecture, we first we talk about the fundamental of polymers, then we explain the three different type of polymers, thermoplastic, thermoset, and elastomers. Polymer, they are a long chain molecule, and each molecule of the polymer has many repeating units which are connected together, and some of them might be 1,000 or even a million of repeating units which are connected all together. And the word polymer is derived from a Greek word. It actually has two parts. One, the first one is poly, which means many, and the second one, second part of it is meres, or we can say mer, which means part. And most polymers are based on carbon element, and they are considered organic chemical. The polymer material, they can be formed, they can be machined. We can do casting with polymer. We can also join them together. They can be different shape. They can be different composition. All these manufacturing processes can be done on polymers. The earliest polymers were made of natural organic material from animal and vegetable product. The most common example is cellulose. Then the development of modern plastic technology actually began in 1920, when the raw material necessary for making polymer were extracted from coal, from petroleum products. The first example of this product was ethylene. Ethylene actually is a raw material, petroleum material. Then a building block of ethylene can be made, so which gives you polyethylene. And ethylene itself is a product of reaction between acetylene and hydrogen. And acetylene itself is a product of reaction between coke and methane. But what are the characteristics of polymers? They are relatively low cost and ease of manufacture. Their resistance to corrosion and chemical is very good. They have low electrical and thermal conductivity. They have low density, means they are lightweight. The aspect, they have high strength to weight ratio, especially when you reinforce them. You mix them with other material, this ratio goes up. They have a good capability in terms of noise reduction, and you can make a different color, and also you can make polymer with transparency, transparent property. There are other characteristics. For example, they have a low strength and a stiffness, and which is not desirable. They also have a high thermal expansion coefficient, and their application is limited to temperature up to 300 degrees Celsius. But for many of polymers, we cannot um, reach to that temperature. So because they will have a low mechanical performance. Mostly the temperature um, should not reach more than 70 degrees Celsius, depending on the composition of the polymers. Here are some of the main reasons for using plastic or polymers in the industry. First, if we want to look at the use of polymers on a volumetric basis, we are using polymers more than metal. And plastic, the good thing about plastic is that it can be molded into intricate parts. Then you don't need further processing. So which is very compatible with the net shape processing. Some of the net shape processing is that we are using these days are called AM, additive manufacturing. And then they are very cost competitive with the metal material because they require less energy to produce if we compare them with metal material. The next good thing about the polymer is that they can be transparent, which makes them competitive with glass material in some application. But if we look at on the negative side of polymers have the following limitation. First, as we mentioned before, they have a low strength relative to metal and ceramic. They have a low modulus of elasticity, which is the stiffness. But in case of the elastomers, this might be desirable characteristic. And their surface temperature is limited to 100 degrees Celsius. And they have viscoelastic property, not elastic property. And another characteristic is that their property degrade. The polymer material itself degrade when subjected to sunlight and other form of radiation. Polymer can be separated generally in two parts, plastic and rubbers. But when we look at engineering, point of view, we have three categories: the thermoplastic polymers, thermosetting polymers, and elastomers. Some examples for this three category: thermoplastic, one of the well-known thermoplastic material is polyethylene. Nylon is the next one, and for thermoset we have epoxy. For elastomer we have natural rubber and synthetic rubber. And here I have a schematic that shows you the family of polymers: thermopolymer, thermoplastic, and thermoset. I should draw another one here, which is elastomer. And thermoplastic are divided into amorphous and semi-crystalline. I'll discuss this in the next slides. And these material, as you see here, mm, thermoplastic can be melted and reused, but thermoset cannot be melted, or for it's a single time melting process. In the next couple of slides, I speak a little about the different polymers like thermoplastic, thermoset, and elastomers. Then I explain these polymers more in detail. First, here we have thermoplastic. Thermoplastic material or thermoplastic polymers are solid material at room temperature. However, they become viscous liquid when they are heated to only a few hundred degrees Celsius. They can be easily shaped into different product. They can be subjected to heating and cooling cycle repeatedly without significant degradation. The next group is thermoset material, and again similar to thermoplastic, we have a symbol for this material which is TS. And this material cannot tolerate repeated heating cycle like the previous category thermoplastic one. When they initially heated, they soften and they flow for molding. This is an example, hardener and epoxy. When you mix them, they become solid material. Then the shape cannot be changed. When they are reheated, the thermoset material degrade or they burn. The difference between thermoset and thermoplastic and thermoset. The response of thermoset plastic to elevated temperature is similar to cake and egg. If the cake, for example, here is baked or cooled, then the reheating does not change, the shape of this cake, right? But thermoplastic is like a butter. You can reheat, and then cool it down, and then it gets a different shape. It may degrade after several years. So this is a characteristic of thermoplastic. The main difference between thermoplastic and thermoset, that you cannot reheat the thermoset, but here with the thermoplastic we can. The next category is elastomer material or rubber. We use this word interchangeably. And polymers, this type of polymer, they show extreme elastic extensibility when they are subjected to low mechanical stresses. Sometimes they can be stretched by 10 times. Then they can recover their original shape. This material is neither thermoset nor thermoplastic. These are somehow between these two. They have the properties between these two polymers, between thermoset and thermoplastic. If we want to compare this three material economically, about 70% of all polymers, the produced polymers, is thermoplastic, and the 30% of all polymers is thermoset and elastomer. On the volumetric basis, the current use of polymer actually is more than metal annually. This outline shows the basic process of making various synthetic polymers. Almost all polymers used in engineering application are synthetic. They are made by chemical processing. Polymer are synthesized actually by joining many small molecules um, together to form a large molecule, and it's called macromolecule. And the macromolecule has a chain-like structure. The small unit is called monomer, and one simple organic molecule, as I said before, is ethylene. Ethylene has this chemical compound. As you see here, this is the raw material with application of heat, pressure, catalyst, or different type of process can be done. Reaction, these are different reactions that can be um, performed here to combine these parts together to make a polymer. You can add filler, a stabilizer, colorant. These are the additives, and depending how you process this polymer, you can have these various materials. The property of polymer depends on the structure of polymer molecule, the molecule shape and size, and the arrangement of molecule to form the polymer structure. And normally polymer are a long chain molecule, which they are formed by polymerization. We have different type of polymerization. It can be linking, cross-linking of different monomer. As you see, we have monomer here, and the polymer of each monomer, as you see. For instance, this is monomer of ethylene, and this shows the polyethylene. Many of this monomer are connected together to form this polymer. And this is one molecule, and same thing for other examples. As you see for polystyrene, we have this molecule, and if we combine them together, then we have this polystyrene. And this is another schematic that shows the same concept. These are the monomer. So each of these monomer can be this block, which are connected together to create a long chain. That long chain is going to be the polymer. The production of a given polymer is generally associated with one method or the other. Here are the two methods we have. One is called the condensation. Step polymerization is another name of this technique, where the bond is going to be between two type of reactomers. So the mers are not similar. But here we have this one addition where the molecule is going to be the same, and the connection occur at both ends of the molecule. So until you get a long chain, which is one example is going to be polyethylene, which is a product of connecting several ethylene together. This schematic shows the addition polymerization. As you see, we have three steps. In the first step, we have initiation, where a couple of molecules are going to be connected, joined together. Then we have a rapid addition of these monomers that will be connected together. At some point, depending on design of this material, for example, number n, when it reaches into number n, so the reaction process is going to be terminated. Here are some of the polymers produced by addition process: polyethylene, polypropylene, uh, polychloride, and polyisoprene. The second process, as we said, step polymerization or condensation. In this process, we have actually two reactions. In the first reaction, we have monomer, single molecule, and then we have a chain of molecule. This one is N-mer, so it means the number of N represents the number of molecule for that chain. Here, so N is gonna let me erase this one. N will be 4. So they will be joined together. It creates this chain. And in the second reaction, we have two different type of chain, N1-mer and N2-mer. Different number. It can be different shape, different composition. Then they will be joined together and create the final chain. And all this process can be proceeding simultaneously. Some of the products of this process is, for example, nylon is one material, polycarbonate is another famous material produced by step polymerization. In the polymer, we have different type of chain. The first one is called linear chain, branch, cross-linked, and network. These monomers, they are connected, they are linked together by covalent bonds. So the type of bond that we have in this link is covalent, and the covalent is very strong the bond, and it's called primary bond. Sometimes polymers chain are held together by a secondary bond. The secondary bond can be van der Waals bond or hydrogen bond, ionic bond, and these bonds are weaker than the primary bond or the covalent bond. The first structure is because the next category, polymer is the branch polymer. As you see the structure of the branch polymer here. The properties of polymers depends not only on the type of monomer, but also on the arrangement in a molecular structure. This type of structure can be found in thermoplastic polymers. Thermoplastic polymers always have a linear or a branch structure, or a mixture of these two the structure. And actually, branches increases entanglement among the molecule, and which makes the polymer stronger in a solid state. They become more viscous at a given temperature in a plastic or a liquid state. And the last point here is that the density of branch polymer is lower than that of linear chain polymer. This is because the branches interfere with the packing the efficiency of the polymer chain. The next structure is a cross-link, as you see here in this slide. The cross-linked polymer, they have adjacent chain linked by covalent bonds. The bond, as you see between this chain and this chain, is covalent through this change. Polymer with a cross-link structure are called thermoset. So all the thermoset, they have a cross-link structure. One example, epoxy has this type of structure, cross-link. And cross-linking actually has a major influence on the property of the polymer. It makes the material hard, and strength of this material is going to be higher than the polymer with a linear structure. If you have a loose cross-link, then the property is going to be similar to elastomer. Another property of a thermoset, or the material with the cross-link structure, is brittleness. They are very brittle, and the cross-link reaction cannot be reversed, so it's going to be changed permanently. The last structure is called network structure, where we have a network of 3 or more active covalent bond, as you see here in this slide, and it's a highly cross-linked polymer. And thermoplastic polymers, they can be cross-linked to obtain higher strength. This process can be done by subjecting the thermoplastic to high energy radiation, such as ultraviolet, UV light, or X-ray or electron beam. It is possible to have crystallinity in polymers. We can have amorphous and crystalline structure in polymers, but keep that in mind. The tendency to crystallize in polymer is much less than that of metal or non-glass ceramics. And also, not all of the polymer can form this type of crystal. And if you have polymer that can form crystal, the degree of crystallinity is always less than 100. In the crystal polymers, we have linear polymers, actually consisting of long molecule, as you see here, with thousands of repeated mirrors. And crystallization in these polymers involve folding back and forth of the long chain upon themselves. This is one example, as you see. And this area that we have crystal structure is called crystallite. And actually, these crystallite can take the form of lamella, as you see here in this picture. They are mixed in amorphous materials. Some part is crystallite, and some parts are amorphous. In polymers, if the crystallinity is increased, then the density is gonna increase as well. The stiffness, strength, and toughness also, they increase. Heat resistance again increases. If the polymer is transparent in amorphous state, then it becomes opaque when it is crystallized. There are some factors for crystallization. The first one is that a slower cooling promotes crystal formation and growth, and the mechanical deformation is going to tend to align the structure and increase the crystallization. When you have mechanical deformation, for example, tensile test, the crystallization during that deformation, you will have crystallization. There are some additives that reduces crystallinity. One of them is a plastizer. In order to import a certain specific property to the polymers, um, some additives can be added to the polymer to improve or modify certain characteristics of the polymer. For example, the stiffness can be increased, strength can be increased, color, all these characteristics can be manipulated by if you use additive material. And additive can change the structure, change the polymer in two ways. First, it can change the molecular structure, and second, it can add a second phase and make the polymer somehow a composite material. And we have various type of additives. First, filler. It can be used to strengthen. It can be used to increase the strength of polymer or reduce the cost of the material. The next one is plastizer, which softens the polymer and it can improve the flow by lowering the glass transition temperature, TG. This term, I will discuss this term in the next slide. And we have colorant, and the colorant are two types, pigment and dye, and these are very fine powder, and these are liquid, and this dye can actually make the polymer transparent. And we have lubricant that reduces the friction and improve the flow, and we have this, some filler that can make flame can make the polymer resistant to flame. Also, we have some polymers that increases the cross-linking process. For Thermoset and Elastomer material, we have some fillers that can be used for these two category. So make the production of these two material easier. And we have also some additive can that increase the UV absorption. And also we have some filler material that can reduce oxidation damage. In the amorphous polymers, actually we don't have melting point, but we have a certain temperature points where the material property, the mechanical property of the polymer is going to change significantly. And that temperature is called glass transition temperature, or glass. As you see here, we have other material like crystalline polymers that they don't have glass point, but when we have a sharp degrading front. This is the temperature that the material degrade. In the next couple of slides, we discuss the thermoplastic polymers more in depth. We explain their properties and their applications. Thermoplastic polymers, they have low thermal and electrical conductivity. They have a low density when we compare it with metal and ceramic. Also, they have high thermal expansion coefficient, almost 5 times larger than the metal and 10 times larger than ceramics. They have low temperature, surface temperature. They have insulator property, as I mentioned before. However, the electrical conductivity of this polymer can be increased by doping. By introducing some impurities such as metal powder, salt, and into the polymer, the um, conductivity can be increased. Also, they have a higher specific heat than metal and ceramic. The mechanical property of thermoplastic is shown here for various metal, and so, as you see, some of them have very young, low young modulus. The slope is very low, but overall their stiffness is very low compared to metal, about 10%. They have low hardness comparing with metal and ceramic. This is because the strength of the secondary bond that we have between the polymers chain between, for example, the linear one. This bond between these chains are secondary bond, and it's not as strong as the bond that we have between these molecules. And also the increased temperature reduce this secondary bond, and these adjacent adjacent chain can freely move on top of each other when we increase the temperature. Here, this slide shows the effective temperature on the strength. As you see, increasing temperature, with increasing temperature, the strength and the modulus of the elasticity decreases, and ductility actually increases. And remember that for thermoplastic, in practice, the repeated heating and cooling causes degradation. And there is one term that they use for thermoplastic. It's called thermal aging of the thermoplastic. It happens when you heat the thermoplastic several times and cool it down back to room temperature. The thermoplastic products include the molded and extruded items, can be fiber and a filament, film, sheets, packaging material, paint, and varnishes. The raw material for the thermoplastic products, for the starting plastic material, are normally supplied to manufacture in form of powder or a pellet. But recently, we are using this thermoplastic material in form of rod for additive manufacturing processes. There are some methods called fused deposition, FDM, fused deposition melting, where the raw material has to be in form of rod. So the rod is going to be more expensive than powder. The least price, I think, is going to be pellet. Thermoset polymers, or TS, they are distinguished by their highly cross-linked structure or covalent bond. We have a chemical reaction that generate this cross-link in the material, and this cross-linking or this chemical reaction is called curing. In the thermoset polymers, always they are amorphous, and also they don't have a glass transition temperature. In the thermoset polymers, we have cross-linking, as I mentioned before, and this cross-linking can be performed in three ways. Temperature activated, so you apply a certain temperature, then the process can be started, or catalyst activated, or you can mix material together, mixing activated. When one of these processes start, then curing is going to be performed. And this curing or cross-linking reaction is irreversible. Here are some of the properties of the thermoset. They are rigid. The modulus of elasticity, or Young modulus, is larger than thermoplastic by 2 or 3 times, and they are brittle. Virtually, they say no ductility. It is capable to work in a higher surface temperature comparing with thermoplastic. It cannot be remelted, but instead it will degrade or burn at a higher temperature. For the thermoset material, you need some sort of energy, for example, heat. Some thermosets, such as epoxy or polyester, they can be cured at the room temperature because the heat produced by the reaction is sufficient to cure the plastic. And the reaction is called exothermic. Exothermic. Sorry for my poor spelling, because again I'm using my mouse, so the spelling is going to be very difficult with this. The next group is elastomer, or rubber material, and we use these words interchangeably, but both they refer to the same material. Elastomer is a polymer that is capable of large elastic deformation, and these polymers, actually this elastomer, can be extended to 500% and still return to their original shape. And the elastomer, we have two different types. One is called natural rubber, which come from plants. The other one is synthetic polymers produced by polymerization process, which those processes that we mentioned earlier that is used to produce thermoplastic material. The elastomer actually is derived from words elastic and mer. They stretch, but they return to the original shape when the load is removed. Some of the characteristics of the major characteristics of elastomers, they consist of long chain molecules that are cross-linked together, similar to thermoset polymers. They have impressive elastic properties. The molecule of the elastomers are tightly curled together when they are not in tension or in stress. And the degree of cross-linking in the elastomer is substantially less than the thermoset. Once the elastomer is cross-linked, then it cannot be reshaped. Or, for example, in an automobile tire, when the large molecule was formed for that tire, then it cannot be softened or reshaped. When a elastomer material is stretched, the molecules are forced to uncoil and get straight. But we have a natural resistance to the uncoiling, which provide initial elastic modulus. But after more load, the covalent bond becomes a major role to resist against a stretch. When we have no greater cross-linking in the elastomer material, the elastomer becomes more rigid, more stiffer, and the modulus of the elasticity is become more linear. Here we have a load and elongation in the elastomer material. It shows the loading profile and unloading profile, and this is called hysteresis loss. Actually, this hysteresis loss gives the rubber a capacity to dissipate energy or dampen the vibration or absorb the shock loading, especially in the automobile tires. We have different type of elastomers or rubbers. The first one is the natural rubber. The base for the natural rubber is latex, a milk-like sap obtained from the inner bark of a tropical tree. And the natural rubber has a good resistance to abrasion and fatigue, but it has a low resistance to oil, heat, and ozone, as well as sunlight. It has a good application in tires, seals, and show heel and engine mount. The next group is synthetic rubber. For example, styrene butadiene. Compared to natural rubber, they have better resistance to heat, and typical application of synthetic rubbers are tire, shock absorber, and belt. Silicone have the highest useful temperature range of elastomers, up to 300 degrees Celsius. Some of the applications of the silicone are seal, gasket, thermal installations, and switches. The next rubber is polyurethane, which has a good strength as well as a stiffness and hardness. It has a very good resistance for absorption, cutting, and tearing. And also it has a good application in gasket, diaphragm, and sheet metal and auto body parts. Here is a takeaway from this course. The three basic category of polymers are thermoplastic, thermoset polymers, and elastomers. We have two methods for polymer production. One is called addition polymerization. The next one is step polymerization or condensation. Degree of polymerization is the average number of N or repeating units in the polymer molecule. And cross-linking is a formation of a connection between the long chain molecule in the polymer. This causes the polymer structure to be permanently altered, and polymer cannot become 100% crystalline. We can add filler to increase the strength or change the property characteristics of the polymer. Thermoset are more rigid and brittle and capable of a higher surface temperature. However, they cannot be remelted. Elastomers and elastomer thermosetting polymers are both cross-linked, but elastomers are lightly cross-linked, and thermosets are highly cross-linked. If you have any question about this lecture, polymers, please send me email or contact me through my phone. This is my office number. I also provided you my cell phone number over email. Have a good time.